Firstly, okay, let's speak about a little bit about MPI sendings. After that, I'm going to consider some behavior or maybe algorithm of sendings concerning your second task. Okay. Okay, thanks. So firstly about sendings. So once I have said that it is not so convenient but may be useful to send data as a whole pack, because in this case the latency, for example, of network will be considered once. If you make several messages, that means that this latency and these waitings will be several times. Okay? So it is latency of the network, interconnection network. Latency. What? Lag. Okay, lag. Latency lag. Okay. So it is rather simple to pack your variables into just array and send this array. But what to do then? You deal with different types. For example, you have one or two variables of int type, integer type, 3 variables of double type, 5 variables of float, and so on. Or maybe you have just one array of integer type and it contains, for example, 10 elements, and you have an array of doubles of 20 elements, or maybe even 1,000, 1,000, and so on. So how to pack them and to send them as a whole, as a one unity?
Well, if there's like lots of ints, we can just send it in an array.
Yes, when you deal with just one type. But if there are two arrays of different types, so there is an answer. You can pack them as a whole thing and send in one sentence, in one message. So how to do that? This is I will show you just simple example. For example, here you can see some integer variables and float array and array of chars, A, B, and some buffer. Let it be that every process will fulfill the arrays just like this. So if there is process number 0, that means every element will be equal to the point counter, and so on. You can see. If the process equals to 0, then B equals to A, and other way, every element of B will be B, and so on. Just to differentiate, to make these arrays different for for process number 0 and for other processes. So firstly, let's consider some MPI function, MPI pack. What it does. So here you can see some arguments. So A is a float type. So I want to pack two arrays A and B in one package. This package will be in the buffer array here. This buffer array is a char array, and it contains 10 elements. So A is a float array of 10 elements. Here you can see 10 elements, type MPI float, and I want to write it into the buffer from the position equals to 0. So from the very beginning. After that, I want to write from the position array B into buffer, and B is contain 10 elements of char type. So here you can see the same position maybe, but not. This position is a variable which contains some position in bytes from the very beginning. When you make one pack, MPI pack function, launch this function, the position, the output position will be automatically changed. So if, for example, there is 10 elements of type float and the initial value of this position was 0, what is the new value of this position? How do you think? 10, and you? What do you think?
Can you repeat the question, sir?
So the initial value of this position, of this variable, is 0. After packing, the new position will be automatically changed. And position in bytes. So how it can be calculated? You can see 10 elements of type float. How many bytes in just one float? 4. Okay. So 10 elements, and each element 4 bytes. So how many? 40. Okay. So this is the output value of position. Okay, we can check.
So what does this 100 mean though? After buffer and then just write 100.
This one?
Yeah.
This is the amount of elements in buffer.
So the maximum amount can be 100.
Yes, because our buffer is 100 elements inside.
Okay.
So let's check this position. So we think that it must to be 40. Let's see. Okay. Packets. So you can see where so the process 0 says that position equals to 40 and it must to be 40. Okay, it's okay. Yes. So as we expect. So after that we saw that position have changed its value. Now it is 40, and from 40 position, after these 40 bytes will be written new 10 bytes. Why bytes? Because this B array contains chars. Every char, how many bytes? Just 1 byte. So after that position will be?
Of course, increased by 10.
Yes, and will be?
Because 10 bytes, 40 plus 10 bytes is 50 bytes.
Okay, 50. We expect 50 bytes. Let's see. So you can see must be 40 plus 10 equals to 50. Okay, we'll see. Position 40 it was a new position 50. It must be 50. It's okay now. So we see that our buffer contains some elements. Here are 40 bytes, and this is array A, and type of this array, type float. Yes, float.
Didn't we say that we allocated 100 bytes to it?
Because this is 100, it can be larger.
And it's buffer, it's not allocated yet, but we can allocate it. We cannot go
Yes.
100 and 1 bytes.
Of course. And here, this buffer is rather long, 100 bytes, and the type of this buffer is char. And after that, after A, after 40 bytes of A, there is 10 bytes of B array, B, and type char. So we can see that we construct new array, some buffer, and it contains different, it contains elements of different types, and so on. You can add into this array doubles, chars, it doesn't matter. So the main point is that you have to consider this buffer rather large, and that's all, I think, because position changed automatically. Okay, we can see some additional information. Follow 22 minutes. Not. I was asked you to not to go here, to come rather late, just to please be in time. If there are no necessary things. Okay, so we can, this is addresses of the array A, of B, and address the beginning of A in buffer. So in this case, we can see the differences in addresses, and we can see that these arrays different, and address B in buffer, and we can see that these addresses differs in 40 bytes. Okay, let's see. Comment these outputs. Okay, you can see.
It's like a pointer to a place.
Yes, so this is address in 16. So decimal 16 oct. Hexadecimal. Okay, hexadecimal system. You can see that addresses of A and B are different. So we, I think, okay. calc. We can calc, and not engineering, but like this. Like this. No. I want to make difference between these two addresses, A00 A00 minus 8D0 minus A00 minus so you can see that the addresses they are different, and the difference between initial addresses of A and B equals to 304 bytes. It doesn't matter. So the main thing is to make difference between these two addresses. This is address of the very beginning of our buffer, and B is the address of first element in this buffer, which is from where information of B array begins. How do you think, what is this difference in decimal?
Maybe it's like how far away this buffer is from the other buffer, the distance.
You said 40, right? You wrote the address as 40.
Yes, 40. Here. So this is first address, and this is second one. 40, yes. Okay, let's check. 40. 28 in hexadecimal system. It equals to 40 in decimal. So 40 bytes. Okay, we can see that the difference. Okay, we check another way. We have checked another way that there is a 40 bytes between this point and this point. And so okay, it's okay. Now let's send this buffer. To send this buffer, we have to use new type, which is called MPI packed, because we have made new buffer packed array, and we want to send this packed array because it contains different types, and MPI wants to know how many bytes it should send from the very beginning of this array, because how it calculates the size, number of elements and times the amount of bytes of one element. Now we can send this buffer of 10 elements and type of this buffer, let it be MPI packed, to process number 1 and take number 1.
What's second one, sir?
Huh?
What's the second one?
Second one where?
So above 100 MPI pack 1, 1. So
Okay.
this, yeah, what's the second one?
You have to know this.
Yeah, I forgot.
Oh, forgot. No. What is this first?
So this is number of process.
Number of
and that's the second one is flag.
Some flag, tag of the message.
I never understood what does, like, I understand it's tag, like positioning.
Just number, some number.
But what's the point, like?
What's the point? Have you, okay, remind last class, and there was some constant any process, any source, any tag. So if there is, for some process, if there is no difference, the order of messages from, for example, one process, and maybe in this process there is a branch, if and two branches, for example. In one branch there is one tag, and on another branch, for example, another tag.
Just know what process we're on, just for ordering, just not to get confused. So one branch is one, and after it's two, we'll never confuse the two branches, basically.
Yes, okay, let's another way. Let it be like this. For example, this is process 0, this is process number 1. Here are some if statement. So there is two branches, and this is some condition. I don't know which one, it doesn't matter. And here, this process sends here something, and for example, with tag 1, here tag, or from the second one, from second branch, it sends something with tag 2, for example. Because here can exist just one branch concerning this condition, first one or second one, and from process number 0 there is just one message when it works. Yes? Here should be received some message from process number 1, and here tag. Which tag should be here?
Well, the one that we received from.
Yes, but which tag? Because the number of tag depends on the condition. So which tag, for example? Here we can write any tag, constant.
So 1 or 2?
1 or 2. This is the first point. The second point, we can consider, okay, with if there is some error maybe during sending, and using status, for example, we can know about in which message this error was. Because, yes.
Can we have two send functions with the same tag, or will it create an error?
No, we can. Okay, we can use here the same tag.
Okay.
This is not, will be there is will be no any errors.
But then the status is going to be a problem, because if all of them have the same tag, we don't know what failed.
Yes, yes, of course. But if we use here just 1, 1, here we also can use just 1. So the text is to differentiate messages from one process if there are a lot of them.
But my question is, when we have this if condition and we have two branches, right?
Yes.
The first send and the second send. So, of course, if we have two branches, different send, so the first send does a different operation from the second send.
Why? Why different operation? This is the same sentence but with different information, maybe.
Oh, okay, yeah. So send different information. So what if in the receive we just want to receive the first one? So why can we put tag 1 or tag 2? So suppose the send 1 with tag 1 sends information. one information, and when the tag with tag 2 sends different information. What if you want to receive the first information only? Then we have to write tag 1.
Because if there will be branch 2, and the process number 1 will send with tag 2, and we receive just tag 1, there will be a deadlock, because we cannot receive. This process number 0 will never receive this information, this message, because there is different tags.
Yes, I understand.
Okay, so let's back to our source. So, okay, we sent our buffer to process number 0. Okay, just forget about this. Like this, a little bit later. So, when process number 0 sends buffer to process number 1, we have to consider process number 1 where it receives this buffer. Okay, because the buffers are in all 2 processes, okay, we just write information into this buffer of 100 elements, and we also use this new type MPI packed from process number 0, tag equals to 1, and the name of communicator. That's all, yes? So now we can, this is just receiving, but we want to somehow print array A and array B into process number 1. In this case, process number 1 should write new information, receiving information of array A in its array A, and information of B in its array B. So firstly, we just receive, and to check array A in process number 1, we print the elements of this array. After that, the position should be equals to 0. We unpack from buffer of 100 elements. From the 0 position, we unpack in array A 10 elements of float type. So now we, from received buffer, we unpack this information into array A. After that, we unpack from the new position, and we know that new position is automatically changed independence of types and amount of elements of this type before. And we unpack into the B array of 10 elements char type char, and we want to see the array B before unpack and after unpack. Let's see. Okay, process number 1, its initial array just before unpack. Oh, 0, yes, 2, 3, oh no, 3, 4, 6, 8, 10, and so on. Why is it so? Because every element, if rank equals to 1, so it will be 2, and every element will be counter times 2. Okay. After receive and unpack, array A will be 0, 1, 2, 3, and so on. So this is information from the process number 0. And we see that receiving and unpacking was done correctly. Array B before unpacked, you can see just B letters. Why is it so? Because if rank equals to 0, array A contain A letters. If in any other process, B contains B letters. So we can see before unpack it was B.
And then of course after attacking the different ranks.
This is correct. Okay, so let's play a little bit. For example, let's play and change position. Okay, this automatically value of this position after first pack, as we can, it was 40. Now we changed this 40 value to 36 by hand.
So now you're going to basically point to the 9th float.
Yes, 9th float. And let's see what will change. So you can see that the last element was lost.
Because it's a very big number.
Not, this is not very big number. Because here we try, process number 1 tries to output float, but here is char. Is the first element char? Okay, first 4 elements, which is AAA, AAA.
It's not like it's trash, it's not like it points to something.
Yes, here will be different thing. For example, okay, buffer. This is 40 bytes. Okay. This is 36 bytes. This is 4 bytes. Yes, 4 bytes. From this position, we write array B of chars. So here will be A, one char, A, and A. So it will be 4 chars, 4 bytes.
So basically calculates the hexadecimal of the chars and outputs it.
Yes. A, 6A. So here you can see 6A. And for A, 4 letters A here.
Oh, that's their encoding.
Yes, something like this.
Okay, I understand.
So we just here we can unpack. Okay, we unpacked 4 T elements into array A, and we can see that the last element was lost because this last element contains 4 letters A. Now let's unpack from B. We unpack from our buffer. firstly, we unpacked these 40 elements in A, and this, the last one, in B. But this here was some garbage, and we just see 6 letters A. Now we want to unpack, let it be 40 bytes in A, and after that we want to unpack 10 bytes in B. And so we expect that all our array B in process number 1 will contain all 10 letters A, because we move the position from 40 from here back to here, minus 4 bytes. Here, new position. We unpack 40 float or 40 bytes of array A, and then automatically this position will be 40, but we change this 40 into 64 and use this new position here, new position here, and we expect we unpacked all 10 letters. Let's see. So we can see all 10 letters here, because we move new position, and we make new position.
So there were 6 before, and then we add another 4 positions.
Huh?
So there were 6 before in array B, so we moved 4 positions, and we allowed them 10 positions, 2 bytes. You know what
10 bytes.
Yes.
10 bytes, yes. And maybe. So another one interesting example is here. Another way to use this spec in different ways. So you can see, for example, some j and I variables of type integer type, and we make the same position equals to 0 and packed into the new buffer double F also 100 elements, buffer of char type, so it contains elements of 1 byte. And we write into this buffer first variable of type integer, so the new position will be 4. After that we write into this buffer another variable j, new position will be 4, and we send, for example, we just write here not the whole buffer, because we know that there is just 8 useful for us bytes in this buffer, and we say send just these 2 bytes, buffer 8 bytes, not the whole buffer, MPI packed to process number 1 and tag and flag 0, yes, tag equals to 0. After that, so you can see new array AA, double A. This is of integer type. In the first case, we receive using just MPI packed type. But now we know it's just for practice or just to understand, and not into maybe your practice will be just for just interesting thing how we can manipulate with some types and sendings and so on. So we know that okay, and these two elements, they will be like this: 777 and 888, and we print them and receive. In first case, we receive MPI packed, but now we know that when we to this process number 1 from process number 0 was sent package containing just 2 8 bytes, I mean 2 variables of integer type. And here we can receive this information and write directly into array AA without unpacking. And we write here the very beginning of this array. We want to write into this array 2 elements of type integer. This will be just 8 bytes from process 0, flag or tag 0, and so on. And let's print what will be. One minute. Let's see, and then back. So before it was 777888, and after it is 100 and 200, as it was in process number 0. So we receive and somehow unpack simultaneously. So what was your question?
I just want to see the code again.
So we sent 8 bytes, and these 8 bytes equals to 2 integers, and we just directly write this packed message into our array without unpacking. This is just understanding of how it works. Maybe it will not be in your practice, but it is rather interesting, I suppose.
That makes sense.
Yes. So that the information I wanted to speak about a little bit about how we can pack and send information of different types. Okay, to make the sending time less than it can be or should be, so to make some economy in time.
So this is not like the second part of like changing 777 888 part. We're not going to really use it in practice. Really
maybe somehow can, but maybe yes or maybe no. I don't know. But we can imagine some situation, and we can, and you know about this specific way to manipulate with this packed message, for example. Maybe it will be useful somehow. I don't know. Maybe. But if you know, it's okay.
Yeah.
So, any questions? Gabriel? Gabriel, do you have any questions? Yes. Or he makes some breakfast, I don't know. Maybe. Okay. So let's continue our considerations and turn to our second task, I suppose. In your second task, we have to divide our array of temperatures into parts. Yes? This method is called domain decomposition. In Russian, it will be like geometry parallelism.
We have to divide our array
into parts. So, what does it mean? Domain decomposition. Here, this our road from 0 to 1, and domain decomposition means we divide this road in special domain, geometrically, something like this. And there is some specific consideration of such decomposition. It is a simple concept. It is called as Fox wall. I think it will be in English like this. Something like this, yes. What the point? The OYX is a time. And here our small domains in every workers. Here will be, for example, 0, 1, 2, 3, 4 processes. And the concept is, let's every process will put bricks in the wall. Okay. Bricks. And every line of these bricks more what will be every row of these bricks, every row is one time level T1. The second row of these bricks time T2, third level, and so on. So you can see that let it be these bricks, let it be like this. Here 1, 2, 3. Something like this. And you can see that bricks on the second row can be put it if if the first row was not wasn't completed. Like it's in reality, when you put blocks into the wall, you have to finish first row. After that, you have to put bricks on the second row and complete all row. For example, here you can see one bricks on some border, because border not will be straight line, but somehow like somehow not straight line. Let's suppose that this bricks was not here. Like this. We cannot put here a brick because there is no bricks, any brick here. So in this case we have, okay, this process have firstly finish its row, and after that, and it should wait that process number 0 complete this row. Yes? And so
if there's no foundation, then the process is going to fail.
Yes, and in this case we can see the dependencies. We cannot do something if we haven't completed something before. Something like this. In this case, for example, this process, suppose it runs very fast. It cannot do its part of the wall because of these issues. Every time it should wait before every brick will be in the previous row. Okay, this is the concept. I don't know why it's somehow no. Okay, it is called as Fox law, a wall, and visually it is very convenient to think about how we should do in your program, in your task, for example. Firstly, every row, after that the next one, and so on. Here will be T3, for example. But we know that there is some dependencies, I mean, dependency in data. Remember that to calculate new temperature in point I, U n plus 1 in point I minus 1 and I plus 1. We have to know temperatures in nearby points.
That's how it correlates with the brick. If we don't have the foundation, meaning the temperatures before, we can't calculate this.
Yes, yes. This is the same dependencies, but in visual way and maybe more convenient way. Yes, the same, you're right. We cannot put the brick, I mean, to calculate new temperature if there is no any bricks on down layer of previous row. So this is the same. You have to firstly get these temperatures, and after that put new brick. But there is second issue. when there is a border here between processes, first process, the second process, so here we should get, every process should get information of nearby points, of temperatures in nearby points. So in your task description, there is some statement that you should use just send and receive functions, blocking functions, I mean. Yes. Of course, in reality, in real practice, people use non-blocking functions. But to understand of the message sendings, it is convenient. It is useful to think in terms of blocking operations. Firstly, if you know blocking operations, if you understand how they work, you can understand or you can make code using non-blocking operations. Okay, you have to understand more complex way. Okay, so consider these processes. These are processes, and these bricks is information which is in these processes. So some arrays. Yes? How process number, let it be 0. This is left border. 1, 2, 3, and let it be 4. 4 and right border. So suppose the main big array of temperatures was of n elements, and we have p processes. Every such a part will be n over p. Yes? Okay. So how many operations will be in one row of Fox-wall here on moment t1, for example? How many operations will be if they work simultaneously in parallel mode? How many operations will be?
Will be n over p multiplied by u?
N over p, no, they run simultaneously. So this is the, I mean, not the operations, the time.
Yeah.
Time, and times the time of one operation. And this will be the time of calculating every such a brick. But there is some exchanging of information. Every brick should, for example, this process, every one brick should send on the left, should send on the right, should receive from the right, and should receive from the left. Yes? And in general, it should be, for example, 4 times tau sendings. And let the height of this wall will be n. N moments of time. The width will be, the whole width will be which one? Which number or which?
The width is going to be n? No.
Yes.
Oh, n.
Yes, n. Width and the height n. And so the whole computational time will be, this is on one level, on one row, times n.
But sir, why is that 4 multiplied by tau c?
Because every brick, because it should send its first and last elements on the right, first sending on the left, second sending, and it should write in the additional cells information from nearby processes. So another third message and fourth message. So that means, in general, in our under our considerations, there are just 4 sendings. That means here we can write down 4. And this will be the whole time of our computing. In case of one process, what will be? How do you think?
Without multiplied by n.
No, we have to calculate the same, the whole wall. So this our task, to fill this wall by bricks.
So then it should be also multiplied by small n and by big n. And time. N be tau c plus 4 tau s?
Without tau s, because we are in one process and there is no any sendings. So just this.
So this is if we calculate everything in one process?
Yes, T1. We calculate all in one process.
So this is not going to be the optimal time, this is going to be the most optimal time?
Not optimal, this is the time of calculated using just one process. Yes, of course, if you be able to use P processes, yes, and make time TP, yes, T1 will be non-optimal.
And last thing, tau c and tau s represent the time, right?
Time. Tau c is the time of one arithmetic operation, and tau c is some time to send information. It doesn't matter, some time. Tau s is for sending, tau c is for calculating. But can we always get this time? TP. Can we always get this time? For example, let's suppose this order of exchanging information. Consider some templates how you can arrange the exchanging of messages, exchanging of information. For example, first template, if every rank more than 0, we consider this, and this. They can send 2 rank -1, so this arrow on the left, and this will be the first operation. And so on. After that, consider they send to rank +1. After that, they receive from rank +1, something like this, and receive from rank -1. And if rank less than size, we consider this, and this. We want to send to rank +1. Let it be send, and then suppose receive. So what will be in this case? Consider every process from 2, 3, and 1, and doesn't matter. Process number 2, firstly, no, something else, something wrong. We can do without this again. Let it be like this. We can erase this one. Yes. Receive R -1. Yes. It will be more correctly. Yes, like this. If a rank less than on the left, from the left, okay, this will be good. That will be good. So if we consider process number 1, firstly, it wants to send something to process number 0. If the rank of the process will be less on just one unity, it will be the left neighbor. If the rank will be greater on one unity, it will be right neighbor. So firstly, process number 1 sends something to the left, here, to the left. And this is blocking operation. Yes? This is 0. Firstly, it sends to the right. It's first operation. What will be in this case? And these are blocking operations.
There's going to be a deadlock. If we send and we send.
Ron, what do you think?
It's going to send.
So the extension will be?
Yes.
Follow? Huh? Will be deadlock? Maybe yes or maybe no. Maybe rain and maybe snow. Will happen. Deadlock and follow, I don't know, something in the middle. Gabriel, do you hear us?
So he's eating breakfast, so he's having fun.
Gabriel, are you here? Here. Are you here?
It's like a silence, like ghost, are you here?
So, do you hear the difference between here and here? The difference in English will be here the same?
Yes, you pronounce them the same. So here is H-E-R-E, and here H-A-R, so I can hear you. Are you here? It's like the same pronunciation.
So it's just, you can understand something from the context. Yes.
I mean, come here, it's like, don't listen to things, come here.
Okay. So yes, here in this template will be deadlock, because these are blocking operations. Yes. Blocking operations, and here you can see on the same logical level two sendings, send and send.
So we can fix it. Send, receive, send.
Yes, we can, we can fix, but in this template under consideration, TP will be which time? TP will be equal to
infinite.
Yes, infinite. Not this time, okay, TP0 let it be. Yes. So you want to change the order, yes, as it was, okay, something like this, let it be like this, yes. So the second, let it be here, TP equals to infinity, and the second template we just, if r greater than 0, firstly we receive, for example.
I forgot that we were working in parallel. What I was thinking was, after that if loop runs, then this if loop will run. I'm still thinking in serious.
And here, so let's consider this template. So if this one, if r greater than 0, so we are here, and the errors will be different. Okay, so if r greater than 0, so we here, firstly we try to receive this type of error, receive this first operation. If r this how to say so in this the if should be after first if r greater than 0, it tries to receive from the left this is first operation, and if r and send to the left, second operation, so on. But it will wait, every process will wait and will be stopped at this operation, because for example here, process number 3 will be stopped on this operation of receiving, because process number 2 also stopped at this receiving operation, and so on and so on. And process number 1 will be stopped, but a little bit maybe, but because 0 is here, its first operation will be sending, and it will take delta t, some delta t. So they will complete this one operation. After this process number 1 will send to the left, and process number 0 will receive from the right.
So I have a question.
One minute. And also this will be delta t time. They will be the same, but they will be time one after one, time after one. So this sending will be after first one. Okay, what's your question?
So my question is, going back to last class, it doesn't matter if this is send, receive, receive, send, or if we have first send and the second one receive and then receive, send. So if we change the, let's say, the ordering, so you see in the first, if r is less than size, we have send, receive. So if we have an if r is less than size, receive, send, and if r is greater than 0, send, receive, it's also going to work.
Of course.
So it doesn't, okay.
It doesn't matter. We just should make thing or message sending when on the same time or logical level should be send and receive. And that doesn't matter. Send, receive, or receive, send, doesn't matter.
But will the picture change then? If we...
A little bit, of course. A little bit will be changed,
but the same
will be different.
Essentially.
So this time will be, this second sending will be the first sending, will be after. Consider further. First process, it completes these two operations and continue with this one. Send to the right. And you can see that here also sending will be, because process number 1 sends and process number 2 receives, and it will take delta t time. After that, process number 1 continue its operations, and yes, and will receive. And you can see that after first operation here, process number 2 continue with the second operation, and you can see that exchanging will be, and also delta t, and so on. Every border between processes will complete the exchanging, but it takes time. Which time? Which time? How many borders, if we consider p processes, how many borders will be?
P minus 1.
P minus 1. Okay, so it will be p minus 1 borders, and on every border, how many? Okay, how much time it will take to complete operations on every border? 2 delta t, and our delta t equals to tau s, some tau s. So the time of sending at every time level will be 2 delta t, and it will be, let's say, delta tau s p minus 1. Yes?
So what is
T
multiplied by P minus 1?
because, as you have said, there is the amount of borders, and 2 tau s is the how much time it takes to complete operations on one border. So this will be time of sending on one time level. So spending time to complete all operations on one time level, I mean calculating and sending. N over P tau C plus this one, 2 tau S P minus 1. And just one level, and all operations will be n small l n over p tau c plus 2 tau s p minus 1, like this. And in this case, speed up n capital tau c n over p tau c plus 2 tau s p minus 1 and n tau c here, tau c, yes, and here will be n, and let it be like this, doesn't matter. So you can see that the time of exchanging depends on P. We can see that the speed up depends not only network, not only the time consuming on one calculation operation, arithmetic operation, not only complexity, but it depends strongly on P. If P, okay, let it be even like this. We can put P here, and it will be 1 plus 2 tau S tau C P minus 1 over N. If P is great, P is the number of processes, that means that our denominator, this is the denominator, yes? It grows rather fast because of this member. It grows almost as P in square, P squared. Okay, in this case, the speed up will be rather good, but with greater P, it will be less and less, somehow like this. The more P, the less speed up. And by the way, how if there is time and this is process number 0. Process number 0, process number 1, number 2, number 3, 1, 2, 3, 4, 0. You can see that firstly, process number 1 sends to the left, process number 0 receives. After that it sends here, receives. After that process number 1 its operation will be here. Process number 1 sends to the right, and after that receives from the right. It sends to the right, received. Huh?
This is going to the brick layout, as you said, the bricks.
Yes. After that also sends here, receives from the right. Yes.
But sir, how can we do the receiving if there's no foundation? Like below the, as we go up, there's nothing below. So how does it work?
This is not the Fox law. It's similar a little bit, but this is the arrangement of sendings on the one row of the Fox law. Just one row. But what I want to say, let's make these drawings 4. We have 4, yes? Okay, something like this. And this is the border. So we can see that all sendings, all exchanging of information was completed. If look carefully, attentively on this drawing, what we can say about the arrangement, of the order. This line takes delta t. But what we can see, if look carefully, if we draw our every sending, every receiving like this, what we can see?
So it's going to be the same time.
Huh?
It's going to repeat the same operation over and over again. It's going to be the same time, as you can see.
Okay.
Time doesn't change. And it can't go over the 4th rank in our, or the 4th operation in our case. But because it's just not in every case, but in our case. That's what I can see. 3 things.
Okay. Any other opinions from for you, Rowan? What do you think when you look at this drawing? Nothing in your head. Gabriel? Okay. So let it be like this. So can these operations and these operations be in parallel?
I would say.
Can these operations and these operations be in parallel? I mean, in parallel can be completed simultaneously.
I would say no, because maybe I'm not. Maybe I'm not thinking right. But the problem is, what I see is that we are heading into a no. Sorry. Just receive send. So send to send. Well, the red ones are a bit tricky to me because there's send and receive here. I don't like that. But in the green one, it's send and receive and send. So I think the red ones might result in a deadlock, and the green one should be fine. There's no deadlock.
Follow?
Maybe.
I think they can run in parallel.
They
can run in parallel.
They can be?
Yeah.
Okay. Yes, for example, if we consider red circles, in this red circle take part just two these processes, this one. In this second exchanging take part these two processes. They are different. These two and these two, they're different, and they can be run in parallel. They can do this exchanging in parallel because there is no any interceptions. Here are just two processes make these operations. At the same time, these two processes can make these operations. After that, after they complete these two operations and here two operations almost simultaneously, they, for example, process number 3, it can continue its operations and make this one.
So suppose a red and a green one that are adjacent to each other, they cannot run in parallel.
Yes, adjacent no, but you can see, if we consider just 0, 2, and 4, if we continue further, for example. So 4th will be here, something like this, and at the same time you can see that every process you can see, so every if we consider every even process 0, 2, 4, it can exchange with odd process from the right. So we can run right like this. If rank 2 equals to 0, even process, it, for example, this operation can be, the order of these operations can be changed. It doesn't matter, because here you can see sending to the right, and here we can firstly send to the right from even to odd, and after that receive, so we can change the order. Send to r+1, after that receive from r+1. From every even firstly sends to the right, and receives from the right. Else odd should firstly receive from the left. After that, send should send to the left. Yes? Now we have described red circles. And now we should describe green circles.
Things are going to be the vice versa.
What should be?
So if the remainder, but if our remainder 2 does not equal to 0, then something happens. Else something else this happens. So suppose
Continue these two. So 2 operations and 2 operations.
then it's R. So
Here.
Yes.
Here.
So here it should be blitzers red, and then wait. Here it should be maybe receive R-1, send R-1, and then in the else it should be send R+1 and receive R+1.
You're right. Except you have here to describe a little bit differently process number 0, because it can't receive and send to the left.
So maybe it's small if condition. So
Rank not equals to 0.
And if rank equals to 0, then we just continue or break the
Size -1, but it doesn't matter. And you can see on the same logical level, sending to the right, receiving from the left, receiving from the right, sending to the left, receiving from the left, sending to the right, sending to the left, receiving from the right. It's okay now, without any deadlocks, and you can see because of all these operations completed simultaneously. That means this operation, how much time does it take? This one, delta t, this, yes, this, and this, and here here delta t, it is the same operation, and the whole time t exchanging s on one time level will be, how much time will be on one time level?
On one time level should be 4 delta t.
4 delta t or 4 tau s. Okay. So arrange. All time consuming for our calculations will be n small, n over p, tau c plus just 4 tau s, and the speed up will be no, let it be like this, n tau c plus n 4 tau s, and will be 1 over p plus 4 tau s tau c n. By the way, take your attention into this line, n over p tau c plus 4 tau s, and remind
What's the starting time we got?
the starting time. No.
What is the third one?
Oh, here. So now, using the third template, we achieve this consuming time. Using first template, the consuming time was infinite. Using second template, our speed up was strongly dependent on p. Okay, this time, the more p, the more time for the exchanging. And here, not here. Well, no, yes, this is third template. Using third template, we can see the time of exchanging messages here is a constant, and it doesn't depend on number of processes. Constant. It doesn't matter how many processes do you use. The exchanging time will be the same, and this is a very, very good point, even if you use blocking operations. So now you can see, in different way, when you use blocking operations, you can achieve infinite time of exchanging time, which depends on number of processes, and we achieve time of exchanging time depends on nothing. It's just a constant. 3 different results. Understand? Okay. So turn back to the description of second problem. So you can see fourth point. Daniel, is for you, for example. Fourth point. Think about how to organize the transfer of messages, how to organize the exchanging of information to get proportionality between, each time step, total transmission time at each end, at each time step. This is the whole time of exchanging on one row of Fox wall on one time level. So what does it mean, O capital on 1?
This is time, big O of 1 with the constant time.
Constant time, and O?
Linear time.
Huh?
Linear time.
Linear time. So now, do you understand why is it so?
So this is the delta T, that's why.
Yes, now we can see this time, exchanging time on each time step. Now you can see this time for tau s is a constant.
Yes.
X, and it equals to O capital 1. This is constant. And here you can see or even like this.
So all these are also constant times. Oh, linear.
Linear dependence. So now, I think before this class you were confused about this fourth point. Yes?
Yes.
Fourth paragraph about this.
Yes, sir. That makes sense.
But now,
I was confused about the whole paragraph.
The physics part. Yesterday, Udo and I were decoding the physics.
okay, now so about fourth, now you understand.
Yes, sir.
So let's speak about physics. Okay, what's your questions?
Please, Udo. What did you ask Alfie last night? What was your question towards the physics part of this aspect?
Or maybe not about physics, but okay, what are your questions about this task? Not maybe about its physics, not maybe about this paragraph.
No, so the first one I understood fully now. That makes sense. Well, the hardest part, I don't know, for me was to still work with the formulas. So
about concerning this one.
Yeah, for example, yeah. So it's it takes quite a long time to maybe understand fully the formula and actually putting it in code. So it might be that might be one of the problems.
This is the simplest one, the simplest problem. And this is, if we consider carefully and attentively on this formula, it is very simple.
Yeah, I think that's the key word. We have to be careful and attentive. Look at it fast and then it's oh.
Okay, so I can describe this formula once more. Okay, so what does it mean? U on x and t. Okay. U on x and t. You can calculate temperature at definite time in particular point. If we consider our road and some point I, it doesn't matter which point. So that means we know x. We know x. Yes? Okay, so this will be some constant in our formula. If we want to know the temperature in this point at definite moment of time, for example, 1 second after the beginning of the process, that means T will be some constant. Yes? Look at this formula once more. So you can see how can we so you can see, yes? So here will be constant. T will be constant. Yes?
So x and t are both constants.
Yes, because at particular point, at definite time, moment of time. So that means I will be, so here constant L, constant equals to 1, yes? P, constant. T, constant. L squared, constant. K, constant equals to 1. P squared, constant. So all values in circles are constant. So you can see, and this is this fracture also constant. So in particular point, you have to variate just m. Here will be something like this. U xt will be some constant, yes, and it will be some sum. Let it be some function on m in this case, yes, because every other variables are constants and the independent variable is only m. M is the number of in a term, number of term in the sum.
Okay.
And it will be sum of f on 0 plus f on 1 plus f on 2 plus f on 3 plus f of 4 plus and so on. So every other variables in this expression, constants, are constant except m. So m equals to 0 will be here 4u0 over p times sum just 1 squared t times sinus p x plus here m equals to 0. Now m equals to 1 will be exponent minus p squared 3 squared t over what?
Over 3.
Over 3.
As m increases, it's going to be 4, and no, sorry, it's going to be 5, then it's going to be so on and so forth, 7 and so on. Okay.
And times sinus,
5,
which one? Pi?
Because now it's going to change a bit. Pi and then 2m, which is going to be 3x, of course.
And
over alpha.
L equals to 1, x. L in our task equals to 1. And so on, and plus
Then does it go on?
m equals to 2. That's all.
Okay, so I think I'll finish up now.
But your task is to make a decision how many terms will be in this sum, because here you can see infinite sign.
So we need to decide when to stop.
Yeah, where to stop? Where to stop?
Let me just look at the question one more time to make sure that
Do you understand now about this formula?
yes, fully so.
And one minute. So now we can calculate temperature in this particular point at definite moment of time. Okay, the moment of time under consideration is known. T equals to something. I mean T capital equals to something is definite. Now at this moment of time you can calculate temperature in point x, some point x. Now when you consider another point, in this way you just change this x. If x equals to 0, that means the very beginning point, point in the very beginning of the road. That means x will be equal to 0 and sinus will be 0, and you can see in every moment of time sinus in point 0 will be 0 and all temperature will be 0. And it makes sense because on the left border temperature always 0. On the right border, if we consider x equals to L, that means sinus will be P times something, and this something is always odd. And in the same point, and in the same, if P times odd, it doesn't matter which odd, yes, 1 or 3 or 5, sinus will be sinus 3p, for example.
Sinus 3p?
Okay, sinus p.
So sinus p, so sinus 180 degrees. So sinus 0.
Sinus, okay, sinus.
It's going to be 0 as well.
0. Sinus 3p.
Also 0.
Also sinus 5p. It doesn't matter which value will be, I mean 2 times m plus 1. This is always be odd, and sinus and at the very end of the road will be always 0. And it makes sense because on the right there is always 0 temperature because of the big outer body. And so on. If x equals to L or L over 2, so the middle of the road, that means sinus will be p times odd over 2. For example, sinus p over 2. What is the value of sinus p over 2?
Sin pi over 2 is going to be 1.
For example, always b will be 1. And the value will depend only on the expression before sinus, exponent, and so on. So, here, in this manner, you can calculate temperature at definite moment of time at every point. Here, 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 here.
If we get to I, it's going to be 0.
Yes, it doesn't matter.
So what we're interested in is calculate between 0 and I. This is what we're interested in.
So you have, it depends on the accuracy. For you, if we see the task, for example, display the temperature value in 11 included each points. So, and compare it with the exact solution. That means there is 11 points, 2 on the ends and 9 inner point, 3, 4, 5, 6, 7, 8, 9. Okay. This will be some delta x. Delta x will be 1, the length of the road, over 10. So you can calculate every x. X here will be delta x times some I. And I will be, like this, 4I from 0 to I, for example, less than 1 from the very beginning of the road till the end of the road, and step will be plus plus. So x will be delta x times I, and you can use this x to calculate temperature in analytical solution, exact or analytical solution, and so on.
And you only need to do this at time equals 0.1.
But the sign is also written here, time.
Yeah, so only at that time.
Which time?
Only at the time t equals 0.1.
Da, yes, of course.
Okay, sure, I understand. Good.
Okay.
I think everything else we discussed was not last, but last, and I think. Okay, so fine. I think that, when is the deadline again, sir?
Deadline, 1st of November, I suppose.
Okay, yeah, I think that's fair. 1st of November? That's good. Okay, I think it is possible to do. But so the next class, can we come and ask questions? I think we're already going to.
Yes, we can consider. Okay, now, why are you smiling? Yes, you. Why you are smiling?
Because
A girl talked to him.
I understand it now, so
Okay.
How about the girl?
yes, that's right.
So let's try to solve this task. Okay, I think that you will encounter with some issues, with some problems, and let's consider your questions and problems once more next class, and maybe even let's this class be completely practice class. So if you have some questions or problems, I can answer, and you will try to solve these issues just on the class, and write your program and solve your problems just in class, and we'll see will you solve or not, and we'll see the result, and maybe all the problems will run correctly, and it will be very well. Okay, but it will be considered on how many people will be. So maybe we consider, I don't know, maybe new term or maybe some MPI things, because it will be the end of October. I don't know.
But if people don't come, it's kind of their problem in a sense. They don't understand.
They can see the record,
Yeah,
but I mean, if there will be a small amount of people, that means we can solve your problems rather fast, and there will be, I think, time to consider something else.
Yes.
So that's why. But if there will be a lot of people, or maybe even remote connection, we will not have enough time to consider something new. Okay, so the plan of our class is complete, is finished, but maybe do not hurry. You have another question. Maybe we can consider this task. Maybe you do not understand clearly what it is about. Maybe repeat something.
For me, I have all the notes, so for me I'm fine. I have everything written down.
Okay, this is what about you, and maybe Follow and Ron have. So you do not have any questions. And Follow.
It doesn't look like a person who has questions. He figured everything out. Not that. Yeah. I think. Yeah. But I think for next time, I'm already going to be able to present some code. I think I'm able to have the basis for it. So I can start presenting.
And maybe it will be useful. By the way, what is it written here? Think about how to organize. Yes. Now we already thought about this, and we know, and they understand, and maybe for you it will be useful to try to make two chords. The main chord will be the same, and maybe difference will be just in the arrangement of data exchangement. And let's try to make these two ways, O1 and O on P.
So for point 4, to try to do
two parts, that. Yes, two cases. And maybe it is useful for you to get a template to this task. A template, I mean the solution of this task on one process.
Yeah.
Yes, that would be very helpful.
Because now it seems that I have this template. Where is it? Like this. Let's consider. I think this is the template. Yes. Time total time, delta t, almost the same. But this is template for just one process. And you can see these two elements, dummy elements. Do you remember where information from other processes will be written? So initial conditions u0, yes, this is the template. u0 equals to 1, initial value. So we have to consider the main point here is to consider just two arrays of temperature. Temperature on the base level and temperatures on the next level. If you want to consider or to store all temperatures along all time through all time, that means you will need maybe a lot of operational memory. And if you consider big 3D array or 3D detail, some detail, and you want to store all temperatures through all time at every point, it demands a lot of memory. So the main thing is to operate with two layers, temporary layers and the next time level layer. And after that, every layer should be written into the disk, hard disk, I mean. And it is not necessary to store this information into operational memory. So so that's why there is just two arrays of temperature, one layer and the next layer. And after you calculate the next level, it should be the base level, and they should change the order, something like this. Boundary conditions: 0 from the left, 0 from the right, both for two layers. Min loop on time, if time less than time total. Okay, you consider temperature and at each point, at every point. This is the finite difference scheme that was written in the presentation. And here you can see, this is the simplest way to understand, but you can do like you want. Here, not the best way to change the layers. Yeah, it doesn't matter, but here you can see that when you calculate next level, it should be the previous level for the next level, and so on, every time. And every time you change the order of these layers and use just two arrays to store temperatures. Okay, and that's all. You print the numerical solution, and here you can see the calculator of exact solution. Okay, we even can launch this. I can't see here heat temperature. Heat temperature, template heat. No, why that's all? Something, okay, now it is here. Heat template. So we can see heat template here, and let's MPI without. Like it doesn't matter. Like let it be like this. Heat, no. And we run it in usual way, by the way. You can see numerical solution and exact solution. But here you can see that there are 51 points, but in the description you should print information just in 11 point, just for simplicity. So you can see that template is working. It works, okay, it works, and you can use this template as a base to write your own parallel program.
Can you send it to us in Telegram chat maybe?
Yes, of course.
So if we can use this template to write for n amount of processes.
To multiple processes, yes.
Okay, so
Okay, that's all.